So my name is Dan, and I work on the Big Data platform. And today we're going to be talking a little bit about our cloud-based analytics infrastructure. Just to give you a quick overview, what we're going to talk about first is just what kind of data we're talking about. Then we'll go over some of the metrics around our scale, walk through the architecture of our platform in the cloud, and then the two main topics we'll be covering is data warehousing and orchestration, which is Genie. And finally, we'll have plenty of time, hopefully, for Q&A. So the first thing I like to say when I talk about data at Netflix, when we talk about analytics, it's actually not the data that most people think of when they think about Netflix. So you think of the streaming data, the actual video or audio content, and that's not what we're talking about here. What we're actually talking about is all of the microservices that we have out in the cloud, the client devices, marketing campaigns, all sorts of different resources that are funneling data back through our data pipeline to our back-end services. So it's not the video streaming data, but it's a lot of other kinds of data. And why do we do this? Well, Netflix is actually a very data-driven company. We like to make decisions based on evidence, so we don't want to make changes to the platform that we can't substantiate will actually improve the experience for users. And this can be somewhat counterintuitive because a lot of times you have a feature you think, oh, everybody's going to love this, but it can actually make it more confusing. It can get in the way of people finding content that they actually want to watch and degrade the experience. So we want to make sure that we actually do things to improve the platform. So one of the things that we do with this data is a lot of A/B testing. So we test lots of new features, ways of navigating the UI, what we show users, different algorithms, and all of this is done with different cells, just like many companies do right now. But the idea is that we can collect all of this data through our pipeline, through many different tests, and then we have systems like this. We call it our Ignite platform, but it surfaces this data from our data warehouse in ways that data scientists can actually evaluate the data and choose the right kind of pushes to make to our platform. Another thing we do is we collect information about how well the video is actually streaming. So we publish the ISP speed index. This gives people around the world a good understanding of how well their ISPs are performing and what service you should be going to in order to get the best Netflix content. Another thing that we do is recommendations. So obviously we want to make sure people can find the content that they're going to be interested in. And there's a lot of the work that goes into this and a lot of data that is used across different cultures, different countries at this point to come up with the best recommendations for any individual user. So it's not surprising that we frequently say that our biggest challenge is scale. The amount of data that we collect grows super linearly with the number of users of our platform. So just because we add some number of millions of users doesn't mean that we scale linearly. We actually collect a lot more data. We're doing a lot more A/B testing. So we have to be able to scale beyond just what our user base is scaling to. So here are a couple metrics of Netflix right now. So we have more than 86 million users of the platform. We're effectively global. We're in almost every country in the world. So there's a lot of different cultures. There's a lot of different types of connectivity, devices, other things that we have to account for. And then we have over 1,000 devices that are supported. Just about everybody in this room probably has a device that they could pull out and watch Netflix on right now. So that's a lot of information that we collect, along with the millions of hours that we stream of video content. That generates a lot of data that we use that we collect in our analytics platform. So what does our platform actually look like from a metrics perspective? We have more than 500 billion events coming through our Kafka data pipeline every day, and this comes to a centralized data warehouse. Our data warehouse is actually in excess of 60 petabytes right now, which is a lot of data, but we go through this data very quickly. Like the event data that we bring in, we typically delete very quickly just because it doesn't have a lot of meaning beyond, say, 3 months in a lot of cases. So most of the data gets deleted very quickly, but we ETL that data, we enhance it, we enrich it, and then store it in our data warehouse for analysts to use, and it progressively gets more meaningful. So we read about 3 petabytes a day, and we write about 500 terabytes. So what does our architecture look like? So we have 2 pipelines for how we get data into our warehouse. One is the event data. So these are all those little events that I was talking about, log messages, things. And that goes through our Kafka data pipeline, coming from all the various services we have in the cloud and many other sources. And then we have a process called Ursula. And what Ursula does is it just splits these events and stages it within our warehouse based on the event type. And then also pulls together and merges the files so they're big enough to do big data processing on top of. The other pipeline is our dimension data. So if you're interacting with a device in Netflix, you're likely talking to a Cassandra cluster at some point or another, keeping track of where you are in a show or serving you content. So the Cassandra cluster holds the dimension data. And what we do is we use the backups from Cassandra and Agathis, which is an open source project we created, to suck that data into our data warehouse for the dimension data. And then you have both your dimension and fact data that you can do all sorts of analytics on top of. So the actual platform itself, from the compute perspective, we're going to walk through this. So at the very lowest layer, we have S3, which is where we have our source of truth data for our warehouse. And then we have Parquet, which is our predominant file format, which we use for performance. We'll be talking about this more specifically when we talk about data warehousing. On top of that sits all of our compute layer. So we run EMR clusters, typically everything on top of Yarn, with the exception of Druid and Presto, which are their own separate clusters. But we have a wide variety of compute tools. On top of that, we have an orchestration layer, services that we use to run all of the services across our big data platform. And Tom is going to be covering some of those topics. Then on top of that, we have a whole slew of tools for doing things like quality checks and visualizing the performance of jobs and understanding what kind of workflows you're actually executing. And finally, at the very top for our data scientists, our users of the platform, we have an interface, so a web interface you can go to and launch queries, track jobs, status, schedule things, as well as an API. So anybody can execute this just with Python. They don't have to have any of the actual clients installed on their local machines or in a container or anything like that. They just need a Python API. So what do our clusters look like? So right now we've got two large clusters. Our production cluster is about 2,300 D24XLs. So these are big instances in Amazon. They've got a lot of disk storage. There's 24 terabytes per instance on these disks. And this will be important as well when we talk about the warehousing. The ad hoc cluster has 1,200. This is what people typically will develop different workflows on, or if they're just doing some sort of one-off analytic, they'll run on this cluster, as well as doing some backfill if they need to rerun some data. We also have a whole bunch of other smaller clusters that we use for testing or specific built clusters for certain types of connectivity or workloads. And then Presto for our ad hoc use case. So if people are just doing very quick analytics, iterating on a particular problem, they can do that very, very quickly with Presto. So this launches us into the first big section, which is about data warehousing on top of S3. And S3 is actually not the most common use for a data warehouse within the big data, or at least the open source big data community. Most people run on HDFS. And this goes back to the old adage of keep your compute and your storage together. But we're actually separating those two. So why do we do this? Well, there are a lot of reasons why we use S3. So one is they have lots of nines. They take care of the durability, the availability. They also have a bunch of features that don't exist within HDFS. So HDFS doesn't have versioning. They have a trash, so it's a little easy to recover data that was deleted once. But in S3, you actually have full versioning of all objects if you use version buckets. And so that really helps the users of the platform, so they don't have to worry about tiptoeing around data and making sure they don't make a mistake and delete a whole data set. We can deal with that. We can recover, so their velocity increases. They don't have to worry about, are they going to accidentally do something very bad? And most importantly, and this underlies our entire deployment, is that we decouple our storage and compute. Now, this is mostly just for the warehouse data. Obviously, within the cluster, there's a lot of locality. There's a lot of execution that happens between stages of jobs or in shuffles in Spark. Locality still exists, but our actual data warehouse is separate. And there's a lot of good reasons for this. So one good reason for decoupling the scaling is, or decoupling is scaling. So each one of these boxes represents a petabyte of data. So this is our data warehouse size. Now, if you take a look at all of our cluster resources, all the disk across all of our clusters, and you put that together, and you account for the three-factor replication that you would need probably as a minimum with HDFS, especially in the cloud, because instances, they can come and go, you might have to terminate them, and you don't allow for any buffer at all, we don't have enough capacity in our existing cluster to house our data warehouse. we would need something at least 2 or 3 times the size of our current deployment, as large as it is, just to hold our data warehouse. And then you have all the complexity that comes along with keeping your storage and compute together. And this is a problem that a lot of companies get into, where you have a big Hadoop deployment and all the data is in that cluster, and all the jobs are running on that cluster. And now you need to do an upgrade, and you're trying to migrate people over to the new cluster. And nobody wants to go because the data's not there. And now you have to figure out, well, how do I get the data over to the new cluster? How do I sync this? How do I make sure everybody's running off the right data? And it really decreases the ability for the platform to evolve. So we can move very, very rapidly. We can have different versions of the same deployments out and running at the same time. We can have many different versions of the different compute engines running at the same time. And this allows us to kind of evolve independently of the data. So that's part of what I was talking about in terms of decoupling the compute and storage. Each one of these clusters can still use the production data. So even if we're using a test cluster testing out new features, we get to use production data for that. We don't have to silo this and keep them separate. Now, of course, if you use S3, it's not that it's always going to be better than HDFS. There are a number of trade-offs, and one of those is definitely performance. So there's much more latency in requests to S3 than there are in HDFS, and this can affect jobs in their split calculation specifically. So if you have a lot of directories that you need a list to figure out how to break up your jobs and execute them in parallel, this can take a lot of time. However, this also runs off cluster, so your job is doing most of this work, and it's not impacting the total throughput of the cluster, but it is impacting possibly stages between different workflows. So if you have a Hive job that's feeding into a Pig job that's feeding into a Spark job, you're introducing latency between each one of those. Another area is the actual table scan. So when you're doing some sort of table scan operator within the execution engine, and you're using like Parquet file, it does a lot of seek operations. And those, again, are much more expensive because there's a higher latency for every request that you have to S3. There's also some overhead in the actual read request itself, just the protocol that's being used. But what we find is actually that the performance of these converge as the volume and the complexity increases. So if you're running a job that has some sort of heavy stage or parsing that happens in the initial stage, the complexity of that is forced over onto the CPU side. So you become CPU bound, and your I/O matters less and less to the point that it's effectively the same as running on top of HDFS. So in cases where you have really short-running jobs and possibly reading tiny, tiny files, you can be impacted by just the difference in performance from S3 to HDFS. But if you are operating at scale with large jobs, large input sizes, that diminishes to the point where it's almost non-existent. So how do we see this? So this is kind of a simple overview of a job. Typically, you have a section that happens in the client. This is the planning stage, the split calculation. That can have some impact, and it gets exacerbated by the number of locations that you're actually listing, and how much data is being split in that phase. But then on the cluster side, you really have two areas that are impacted by any performance difference in S3. One is the initial table scan, and then the other one is actually the store operator. But inside that, you have many different stages, and all of those are either using HDFS for like Pig, Hive, MapReduce. With Spark, it's going to be using local disk and shuffling. And then in Presto, it's actually using in-memory. So there are a lot of stages, and what happens is this cost is also amortized over the length of a job. So if you have jobs that are many, many stages, just that impact at the very ends is not going to be very significant compared to the whole operation. Okay, so in addition, so we talked a little bit about the actual data and how we store it in S3, but it doesn't make a lot of sense unless you can you can get to the data that you actually want to. So we have a metadata system that we call MetaCat, and it's a federated metadata system. So you can think of it in terms of like the Hive Metastore, but this is kind of the Hive Metastore on steroids because it reaches across many different systems. It can talk and describe RDS instances, Teradata deployments, Redshift deployments, Druid deployments, and it allows us to get information across all these different systems. But it also exposes a Hive Thrift interface for anything that we can run the big data workloads across. So this means that Hive, Presto, Spark, anybody can talk to it and get a better understanding or an accurate understanding of where the data is located within this large data warehouse. And the most important thing is it provides a logical abstraction over the actual data, because nobody wants to remember S3 bucket some path into a warehouse and then it's partitioned by some values. This is all handled by the actual warehouse. So what does that look like? Well, if you're familiar with Hive, this is a very normal concept. It sounds or is set up very similar to a relational database. So you have databases. So right here we have, like a data science, an ETL, telemetry data, A/B test data, and then within each of those you have different tables. And you can select just by calling out the name in SQL or in using Spark or Pig which one you're looking for. And then the added level of indirection is the partitioning. So this is how you actually structure it within S3. The nice thing about this is it actually overlays very easily on top of S3 in the same way that it works on HDFS. So that partition location is actually just pointing to a path in S3, and all the data for that particular partition is underneath that path. So, of course, the most important thing is down selecting how much data you're actually going to process, and by structuring your warehouse and your tables appropriate, you can really limit how much data you're going to process. No job is going to process all 60 petabytes, but many of them can carve down to just the data that they're actually interested in order to answer a question, and that has a big impact on the total performance of the job. So now we've talked about the warehouse all the way down to a specific location, but how do we actually store the data? So I mentioned we use Parquet very heavily, and there's a lot of features in Parquet that add to the performance, especially on top of S3. So for those who don't know what Parquet is, it's a file format, it's columnar. That means that it's going to take the data, and instead of like a comma-separated file or tab-separated file, it's going to store the column data together contiguously on disk. And this has some benefits. One, you can improve the compression, because data in columns is going to be very similar across the entire column. And so you get really high compression there. You can also do column projection. So if I've got 100 columns in a table, and all I care about is maybe 5 of them, I only have to read the data for those 5. And that's really helpful because it cuts down on the total volume of data that you're processing in the job. So that's nothing particularly new. We've got columnar file formats. They've been around for a long time. But one of the things that Parquet does add is it adds metadata about the actual data that's in the file. So at the very bottom, this is the structure of a Parquet file. So you have the data is actually broken up into row groups. And that's maybe some size of data that you want to hold contiguously together. But within those row groups, you've got column data, and that is what is actually stored contiguously on disk. And what we see here is a file. It has 2 row groups in it, but at the very bottom we have metadata. And what it has is information about each specific column. What is the min value? What is the max value? As well as the areas highlighted in red, which are dictionary pages. So if it can be dictionary encoded, you have a full set of the values. Even though you don't necessarily know how many times it's repeated or anything like that, you know what is actually in that column data. And we can use that, especially when you stage your data appropriately to take advantage of some of the features in the processing engines to either skip or do certain types of operations like counts very quickly. So one thing that you have to do is you actually have to stage your data at this point. So one of the things that we do is you partition by low cardinality fields. So these are things like date or hour or maybe region or something like that, where you're going to have very large buckets of data under each one of those partitions. But then what you do is you actually sort by the very high cardinality fields. And a really good example of this is like telemetry data. So at Netflix we have a system called Atlas. And it keeps track of all the metrics for all the services at Netflix. And they have one column which is the actual metric name. And that's typically what you're going to be looking for, be it latency or throughput or something like that. But there are millions of these different metrics across all the different microservices and ways that they slice and dice this. So if you sort by that high cardinality field, you can reduce the amount of data that you actually read by 100x easily. So what does that actually look like? So if we store our data, you can see if these are all data files, and the data we're actually looking for is all the little red lines that you see there. They're all sporadic throughout the entire data set. But if we sort that, you put all of that data into just one file. And then what we can do is as we go through that, you can filter out just the one file that you actually want to process. Yes, you have to read the footer for every single file, but that's tiny in comparison to reading the entire data set and processing the whole thing. So we take advantage of this with some of our biggest data sets. Like I mentioned, our telemetry data set we do it with. We also have like UI events that we have a common logging So it means that we have lots of different event types, and we use the same approach there. So if you want more information about how to take advantage of these, there was a recent release of Parquet 1.9 that has all of the features that we've been working on. And there's a slide share here with a presentation that goes into great detail about the various properties and everything else. So this will be posted, I believe, after the conference. So if you're interested, you can go take a look at that. So with that, I'm going to hand you over to Tom, and he's going to take you back up to the stack and talk a little bit about our service layer.
Right. Thanks, Dan. OK, so Dan went really low. I'm going to come back up a little bit higher and talk about our Genie service, which is an open source service developed to solve a few problems. And to kind of establish why we developed this service, I'm going to walk through kind of a story of how a data platform might evolve. And some of you may be able to relate with this, some of you may not. So you start out with a nascent data platform, right? You've got a few users. They might log into one machine and access your one Hadoop cluster or whatever processing cluster you have. Everybody's pretty happy. There's enough resources for everybody. There's not much stuff going on. Pretty soon you realize that you need to start testing some stuff, and you need 2 versions of things. So now you got a test gateway, you got a prod gateway, you got 2 clusters. It's not too bad. People know where to go. People may need to replicate data, like Dan was mentioning, from prod to test, but you can still kind of handle the situation. Pretty soon, our company's growing, our organization's growing, we have more users, we need more resources, more client resources, more cluster resources, everything's growing. Doing deployments becomes much more complicated. You don't want to have as much downtime. You don't want to, as you have more gateways, you need to deploy different binaries to these gateways. It becomes very difficult to start managing that. Pretty soon you decide, oh, I need clusters for specific purposes. So Dan mentioned at Netflix, we have a lot of clusters. We have ad hoc clusters in Presto. We have lots of production Hadoop clusters, test Hadoop clusters, and you start scaling horizontally across all these different needs. Then your user base starts maturing. So your data scientists actually become kind of smarter than the people running the data platform. They want to run the new stuff, Spark 2, they want to use R, Python, whatever it is. They start complaining about their job being slow because they're not getting enough resources, or their coworkers starving them out. And you, as a system administrator of your data platform, need to respond to all these things quickly and dynamically. And pretty soon, everybody starts looking kind of like this. The administrators aren't happy, the users aren't happy, everybody starts crying, and people are stressed. So a few years ago, we started developing Genie to solve these problems. We wanted something that, from the administrator point of view, helped us to administer launching clusters, maintaining binaries, all that stuff, and abstracting those details from the users, while at the same time allowing users to have a scalable set of resources to access these clusters and not really worry about where the clusters were, how to connect to them, what to run on them, all that kind of stuff, or setting up a working environment. So I'm going to walk through a couple problems that we face at Netflix from administration and user point of view. For the administrators, we've got a lot of moving parts. And Dan and my team, we're kind of the administrators in this case because we do DevOps. So we've got about 15 clusters. Dan walked through some of them at any given time. We run about 45 different variations of the executables you can run against those clusters, whether it be different versions of Spark, different versions of Hive, different versions of Pig, or Presto, whatever it may be. And then we see a very heavy load of jobs. We run about 45 to 50,000 individual jobs, which could compose of a breakdown of those different processing layers. So one job could actually result in 4 or 5 actual MapReduce jobs or Spark jobs resulting on the cluster. And we've got hundreds of users. So in the talk before this, if any of you were there, they talked about how you have 80 data scientists maybe at Stitch Fix. We've got well over 300, I believe, at Netflix now. So between them and a lot of other people, we're seeing a lot of users. And for users, they don't really care about the details, right? They don't care where your clusters are, what's running. They just want to make sure they can connect and get to their data. We've got a lot of data. They want to do it. They want to do their jobs. They want it to be easy. So how do we kind of merge those problems together and have a solution? That's kind of where Genie comes in our platform. So I'm going to talk about how it comes in and helps the platform administrator, which is our team, which is really all I care about. So the administrators, we want a tool that basically simplifies configuration management and deployment. So when we launch a new cluster, we don't want to be copying around site XML files or configurations about what the cluster looks like, what version it's running, anything like that. We want to minimize the impact of changes to users. This is really important. We have 300 data scientists. They've got a lot of important work to do. We don't want, when we change out a cluster version or anything like that, we don't want them to have any impact in terms of being able to do their job. We want to be able to respond to any problems with the system quickly. So we want to know what clusters are running, where they are, how to shut them down, how to do any of that kind of stuff. And we definitely want to be able to scale the client resources as load increases. So we don't want to be scaling out and sending out a new gateway every time that we need to. We just want the system to handle that automatically. So from an administrator perspective, I'm going to go into the Genie data model. So it's pretty simple. We've got something called a cluster. It just basically represents the metadata about the cluster, which could include things like where the site XML files are located. We personally load them to S3 when the cluster is launched on EMR. Then each cluster can be linked to many executables, and we call these commands. So basically those are what you would, if you were on a command line terminal, you would execute hive, you would execute pig. That's what the command would be. And then each command can be linked to many applications. So the applications represent the dependencies. So it would be a tarball of all your binaries for Hadoop, a tarball of your Spark application, whatever it may be. And Genie will take care of downloading all the necessary dependencies into the working directory for a given job. And I'll get into that in a little bit. It's important to note that each of these resources we have in the data model can be tagged with specific tags. And we use these tags a lot to uniquely identify a cluster and allow users to just set certain tags to say, I always want to run on, say, the SLA cluster, or I always want to run Spark submit. I don't care what version it is, just give me the default. Or I always want to run the SLA cluster. So it allows us to move the tags around from cluster to cluster as the role of clusters or resources change. And I'll get into some of that too. This is just a quick screenshot of the Genie UI that shows how you can search resources. It shows all the clusters that we currently have registered in Genie and kind of their state. You can filter on state and like that. So this is kind of how we as administrators can go and see how anybody is launching clusters and where they live and how to connect to them and that kind of stuff. So let's go through some quick use cases that somebody might want to do on a big data platform if you're an administrator. So let's say you want to update a cluster. The first thing you would do in the cloud is kind of start up a new cluster. You then register that cluster with Genie with a set of kind of default tags, which generally means your ID and your name. But none of those common tags like SLA or anything that would be common across a bunch of clusters. You then run whatever smoke test you want to make sure the cluster is good. Let's say you're testing a new version of Hadoop. You want to make sure all your previous tests still run fine. You would then move your tags over from the old cluster to the new cluster in Genie. So like that schedule SLA tag I showed earlier, you can move that to the new cluster, and all the jobs would automatically load over to the new cluster. So anybody submitting new jobs that wanted to go to the SLA cluster would go to the new one. They didn't have to change anything on their client code. They didn't have to change anything in their UC4 code, anything like that. It just automatically works. And you can let the old jobs finish on the old cluster behind the scenes. Users can still access them because Genie still knows where they're running. You can still work through that. And then you can shut down the old cluster when they're done, and there's no downtime to users in this use case. Next, let's say you want to load balance between clusters. Let's say in the middle of the night, you have different loads. So for Netflix specifically, people watch a lot of TV late at night, but then in the middle of the night, they're sleeping. So our load goes way down. We have a lot of resources available. Well, we may want to move some of our ETL jobs over to a different cluster. So we take the tags that are on our production cluster and copy them over to our ad hoc cluster, because all data scientists are usually sleeping at night, hopefully. So we take the resources that are on those ad hoc clusters, and we put the same tag on both, and now Genie will just start putting jobs to both of them, because they're really the same cluster. It's just how we reference them. Then in the morning, when we say, OK, the data scientists are starting to wake up, we need the resources back, we remove the tags from the ad hoc cluster, and jobs are stopped being submitted to them that should be on the production cluster. And this is transparent to all the clients. They don't really know which cluster their jobs are going to. They just know how to access them via Genie. So, and then usually if you're an application administrator, you want to deploy a new version of Spark, let's say, you have to find all the clients that are running those versions, right? All the gateways, any users that are upstream running Spark or whatever it may be. But you need to update that without any downtime. For Genie, since all the jobs run on the Genie nodes, we can load the new binaries to a central download location. In our case, that's S3. And we can and then Genie will automatically invalidate its cache, and it'll download the new ones on the next run through. And so this will be an instant change across the Genie cluster as jobs are run. So you don't have to actually hunt down all the places Spark or whatever it may be are deployed. You just need to update Genie's configuration, and Genie will take care of the rest. OK, so those are some use cases that were for administrators. Hopefully, most of you can relate with them in some way. So for users, the data scientists, they usually want to discover a cluster for a job to run on. They want to run the job client, which could be Hive, Spark, whatever. They don't care about where your dependencies are. They don't want to have to install Spark. They want to install Hive. They just want it to run. They want to be able to check on the status of their job easily, obviously. They want to view a history of their jobs to see how their performance changed over time. And they obviously want to get their job results. So I'm going to walk quickly through how job submission to Genie works, just so that we're kind of on the same wavelength here. So you're a superstar data scientist, and you have your boss wants you to create a report, or you need some sort of new report on an A/B test, and you're like, I need to run a job. So you submit a job to Genie, and basically two of the key fields in any job submission are these cluster criteria and command criteria, which leverage those tags I discussed earlier. In this case, the user wants to run on a yarn cluster. That's the SLA role, so kind of your production cluster. They don't care what it is. They just want the production cluster. And they want to run Spark version 1.6. That job submission goes to Genie through the REST API. And Genie accesses its RDS instance, in this case MySQL, to get the metadata about what's available currently in the system. It finds that there's a bunch of clusters and a bunch of commands that are currently available. It'll then compare the tags that are on those resources, the commands and the clusters, to match anything that could match what the user selected. And it finds that there's a cluster that matches and a Spark command that matches. It'll then download all the configurations out of S3. This bucket is supposed to represent S3. My boss told me it would, so that's S3. So all the files are downloaded onto the Genie node at runtime and set up in the working directory. So for that Spark command and for that Hadoop cluster, they're all downloaded into the working directory, which becomes effectively like if you were just sitting on the command line and if you executed Spark, that's your working directory. Genie will then submit the job to the cluster that was selected. It'll run. Your user can go into the Genie UI, monitor it, see what's going on, and wait for it to be done. So hopefully that's clear. So the Genie data model looks kind of like this from a user perspective. Their job is linked to the cluster command and applications it ran with. They can go and access this metadata anytime going forward. A job request, it's kind of hard to see at this scale, but basically there's some important fields in here. The cluster criteria and command criteria you can see, and any command arguments they might want to add to their executable, and you can tag your jobs so you can search them later and that kind of stuff. From a higher level, we've created Python clients, Java clients that users can use to submit jobs to Genie that abstract a lot of the details of those JSON payloads. So in this case, this is a simple example using the OSS Python client from somebody who wanted to run a Presto job. So they're just selecting, you just say what script you want to run, any parameters you want to submit in, and you can run the job and wait for it to be done, just via these few lines of Python. So you don't have to worry about where the Presto cluster is, what the binary that's running is. This is all through service-based access. Once your jobs are done, users can go to this job history UI and look up jobs and go to find the job output directories. So those little file folders, if they click that for their job, they're taken to something that looks like this. And this is basically their working directory. So all their scripts are loaded in there. The output is in standard output. Standard error obviously holds your error file. So it's just like they had their own custom working directory on the box. So there's nothing that the user needed to do to set all this up. Genie downloaded it all out of the configurations and ran the job and executed it on the cluster. So that's kind of a brief walkthrough through Genie. So wrapping up, we've got our data warehouse, which Dan discussed. We use S3 to scale out. It has a robust set of nines, as Dan mentioned. We like to decouple the compute from the storage for all the reasons that Dan discussed, the performance and the ability to run clusters across all the data sets. And we use Parquet for speed to take advantage of the columnar format. On the Genie side, we're running the actual OSS code in Genie. So if you want to run Genie, you can take the same code and run the same stuff we are. We're running about 45,000 jobs a day on those Genie nodes, which are about a cluster of 25 I24XLs in production. And we keep about 3 months of jobs in the database in the job history, so that's about 3 million or so of history. And if you want to see what Genie's all about, you can go to the GitHub page. We've actually created a demo using Docker and Docker Compose where you can stand up Genie along with a couple of clusters on your local host and submit jobs to those clusters, and you can see kind of how it works. So with that, I think we finished a little bit early, so we've got time for some questions if anybody has them. Just don't piss us off, because I don't know. So we don't have a microphone for this?
Yeah, we don't have a mic, so we're gonna.
I can just talk for a little bit.
Yeah, and we'll repeat the question.
One of the questions: how do you handle EMR master failure?
How do we handle EMR master failure? So there's, it does happen all the time. Well, I'm not going to say it happens all the time, but it does happen. And what we actually do is we actually use Genie for this. So one thing that you can do is you can either have a small standby cluster that just has a couple nodes in it that's sitting, idle. And using the Genie tags, when we detect a master failure, we can just reset the tags to the new cluster and issue a resize, and it will go up to size, terminate the old one very quickly. And usually we can do that with very minimal downtime. We also do this with just our upgrades and everything else, where we do a red-black deployment, and we use the tagging in Genie in order to handle that. But yes, it does happen. Next question. Way over there in the corner.
How do you handle ER side?
How do you handle?
Disaster recovery. Do you have a different, have a two systems with two different regions, or?
Two systems in different. So we actually use. We have all of our data warehouse in US East 1. So we bring all the data to one place because that's going to work best for the big data compute. If you're reaching across to a region on some other continent, you're going to see some serious performance degradation. Is my expectation. I've never actually tested it. As far as the disaster recovery, we rely a lot on S3 for the warehousing. That goes to the 11 nines of durability or whatever they spec out. So that's what we do from that perspective. And then the clusters themselves, we run in 2 different AZs. So we can always make sure that we have a sizable cluster in one AZ or the other. And using the tags, if something happened where we lost our production cluster, we could always just re-tag our ad hoc cluster to be the production cluster, and it would start taking all the production load. And while there would be some interruption because it's not as large as the production cluster, at least the critical jobs and everything else would still be able to go through.
So how do you handle access control? Is that what the MetaCat does? And actually, can you talk more about MetaCat?
So the question was, how do we handle access control, and can we talk a little bit more about MetaCat? So MetaCat, again, is a federated metadata service. And the idea behind this is that we have lots of different data systems, and we want some central way of talking to each one of them or getting information about the data that's stored in each one of them. That doesn't mean that you can read data through MetaCat. It's just describing all of the data sources. So you may be able to say something like, oh, we have a Druid cluster, and this is the data that we indexed into it, and this is the configuration for it. So any system that needs that information has one central place to go to. So we do that with Teradata, we do that with Redshift, and it makes it really easy for us to do things like, we have libraries built around moving data from one place to another. While S3 is our source of truth, we want to be able to say, oh, well, take this S3 data, or maybe this specific table and these date ranges or some selection of that, and move it over to Teradata, or move it into Redshift. And so people can just issue very small commands that just say, move H to R, Hive to Redshift, and it will take care of it for you. So that's the purpose of MetaCat. But one of the things it also does is it abstracts something. So you can actually run against Hive Metastore. So it exposes an interface to get metadata in the same way that all of the big data compute engines that are out in the open source typically expect to see it.
Did I hear you correctly that you're not concerned about backing up your production data because of the reliability of S3?
So I'm not saying that we're not concerned about our data. I mean, there's always disaster cases or potentially malicious cases where data will be lost. What we do is we leverage the tools that they have for both, access protection and control over what users can actually do to the data. And one of the things that I mentioned is that we have version data. So we let people soft delete. We don't let people hard delete. So there are things that you can do to ensure that you're not going to accidentally lose data in those cases. But there's obviously the case where there's some giant disaster, and there are things that we're looking into for better ways of backing up as much as we can of the data warehouse. But replicating 60 petabytes is a lot of data to have a second copy of.
Expensive.
I saw some other hands here. Did anybody else have a? Sure.
A couple questions. So we tried Parquet with Spark on S3, and there are long latencies on the read side, super long latencies on the write side.
Mm-hmm.
And then I actually Googled and looked for I guess it was Strata Talk that you guys gave.
Yep.
They mentioned like the merge schema disabling, which I've heard of. But I think I've also heard of like turning off summarization on writes.
Yes.
That's what actually mentioned in this deck. So like they were like basically finding the right size of the objects written to S3 is one question. I mean,
Yeah.
how do you reconcile the block size in HDFS and then sizing S3 objects? And also, and I can follow up later, but what are the right sets of parameters?
So I'll answer a couple of those at kind of a high level, and if you have more specific questions. So the question was about performance with Spark and Parquet against S3. How do you do the right size of files? How do you set the right options? Some of the options are set in that talk from that was on the slide there. As far as the actual file size, block location doesn't matter in S3 because we don't have any information as to the block size or how S3 is actually carving up the data in the backend. So you don't necessarily want to try and align to certain block sizes. There are ways you can kind of fake it out with the file system for split calculations that may have some effect on how those get divided up. Spark specifically, we actually have a heavily modified internal version of Spark to address some of those problems with the read and write path. We are working on trying to make an open source version of our S3 output committer, which takes care of a lot of the problems that you see with the open source, especially because it tries to treat S3 exactly like any other file system. It'll try to stage its intermediate data there, and then when it goes to commit, it'll copy it into the final location, but S3 doesn't have a copy. I mean, it doesn't have a rename function. It only has copy, so you effectively copy it to S3, then recopy it to S3, and then delete the temporary ones. And sometimes that can happen multiple times. So there are high latencies, and we've worked around that in certain ways. So we use an S3 output committer that actually writes locally and then uploads to S3 as the final commit, and it does that massively parallel, so it's actually quite performant. So any more specific ones we can take offline?
And the last question is vectorized instructions or execution. You don't get the benefit of that when the data is not local.
The vector.
Vectorized, so like Hive, for example, supports vectorized execution.
Right.
But you only get that, I mean, the only value is if your data is columnar on disk fed to your memory bus, into your cache line, into your CPU, and if you're just fetching a huge object, S3 object.
Yeah, so Hive doesn't have support for Parquet with vectorized read anyway. I mean, it's got a vectorized execution, but the read itself is not vectorized. So I wouldn't worry about it too much with Hive. As far as the vectorization, I think that we'd have to look at that more closely because I'm not sure that it is quite linked to actually where it's stored. Because a lot of these systems, like with Spark or Presto, the execution that they do is not necessarily vectorized in the sense of like CPU vectorization. It's vectorized in the sense that they're doing an operation across a lot of data that's in one particular column or maybe sets of columns at a time. And the way that Presto does it, it just bytecode compiles the entire stage or execution that it's doing, and like Spark 2.0 is doing that across all the different, against all the different operators within a stage as much as it can. So it's actually not vectorization in the terms of CPU.
Execution on the CPU, it's like
Right, exactly. Right.
Are you using the summary files for Parquet? Are you updating them?
Yeah, so we actually don't use summary files, and part of the reason we don't use summary files is because we have a metadata service to do this for us. So we entirely do not rely on any of the footer data for split calculation or the summary files for describing the schemas or anything like that. All of the schema information is actually in the metastore, and across most of the engines there is a feature which is called column index accessed. So if you're typically reading Parquet files, you're going to be reading by name, so you're going to be addressing columns by name. But any system that's working with a Hive metastore, Hive traditionally will reference things by their column ordinal. So what we do is there's a flag that you can flip to do ordinal-based access. And then what you're doing is you're basically saying, I don't really care about the file schema, I only care about what the metadata schema is. And that's the way that we work. Any other questions? I guess we'll let you go for the night. Thank you very much.
Thanks.